We are living in trying times for both young and old. Many who have just gotten out of school find themselves stopped in their tracks in a global health crisis that just doesn't seem to end. Independent of that, property prices have gotten so high that a considerable percentage of the population know that they might never be able to buy a house for themselves. And those who already own a home look at the extreme weather events we are facing right now and can't quite decide what exactly it'll be they'll have to protect themselves against. Will it be droughts and wildfires, or floodings and tornadoes, even in the middle of Europe? And others who left school decades ago, they also had to leave another place, and that was the job they used to have. The steel mill was closed, and it ain't coming back. But good to know they are still building new office towers to house all the new lawyers we need so much. To sum it up, if work is both rare, inherently meaningless, and doesn't even seem to offer the chance to build up enough capital to buy property long term, it might be understandable why more and more people don't see a meaning in all of it anymore. And I have often felt like that as well. I remember some years ago lying in bed and asking myself, why even get up? It's all pointless anyway. But listening to my own thoughts, I got really angry at myself and said out loud, maybe the situation seems desperate, but I'll show 'em. The day the lights go out at this place might still be very far from now. And even though I also don't have the answers to the very real structural problems I just mentioned, I have discovered for myself time and again that meaning can be found in the little deeds and routines of your everyday life, even when the entire system around you seems to be insane. You can find meaning in caring for a tiny part of this huge world. That can be another person, a place, or, as in the case of this video series, objects you deem worth saving. And that's why I'll ask you to once again witness how I put a seemingly unreasonable amount of work into just that. So let's see then what we can find on the scrap today. Down here we find an applause sign. And it's not that I'm planning to record future episodes in front of a live audience, you know, but I think this could be fun, so I'm keeping that. This scissor type letter next to it is also pretty cool, but it's very heavy and made from aluminium, which at the current scrap prices would make it too expensive. This power drill over here seems not really worth it, since the enclosure is broken and rainwater has seeped into it for some time. But I also found this Makita power drill here that we will take with us. This old bench grinder is unfortunately beyond reasonable repair. But over here I found this drill stand. Maybe we can use it together with that Makita drill. What do we have here? An industrial size deep fryer. Unfortunately though, it's not of great quality and is also rather disgusting to handle. Down here, however, I found a big coffee grinder, and we're going to take a look at that. I also recently found two other items that we'll repair today. This fine brand angle grinder, and also this rare angle grinder stand. In fact, we're going to build a permanent support for this stand and also make a soft start circuit for it. This video will get increasingly more complex towards the end. But believe me, there will be some interesting lessons to be learned. We'll start with something rather down to earth though, the Makita drill. This is a quite powerful 650 watt drill with a D handle that you can also turn around. This particular model was made in 1998, but a more modern version of this drill really costs a pretty penny, so it might be worth saving. Apart from the fact that it is very dirty and there is still an old wire reel stuck in that chuck, the power switch is broken off and the power cord was also cut off. I suspect that the broken switch was the reason that this tool was discarded. I start by removing the wire wheel and cleaning the enclosure with baby wipes, which, as it turns out, is a very effective way of cleaning equipment. The Sharpie markings are easier removed with WD-40 or a similar product. And in the next step I take the D handle off so I can clean it more effectively. With the older models, the motor brushes can easily be taken out in order to replace them. But there is still enough material on them and they can stay. I also take out the roller to look at the windings and commutator, which are looking pretty good to me, and while I'm at it I will also apply some new grease to the gears. I also take the pistol grip apart, and like so often I will use the ultrasonic cleaner to clean its parts, among other things. Inside the handle we can find the filter components. They are not of critical importance, but if they are bloated or cracked, they need to be replaced or at least removed. These ones, however, are still in good shape. Here is the broken power switch. A new one needed to be ordered, and I can't say if it's Makita or just luck, but until now I was able to get the Makita replacement parts I needed for this and other repairs by simply looking for them on eBay. I can't necessarily say that about many other manufacturers. The switch I ordered here seems to be an original replacement part and it fits perfectly. And after replacing not only the switch but also the power cord, we are ready for a test. Do you also remember that we found that drill stand? Maybe not the most exciting find in the world, but it would be a nice addition to the drill, don't you think? Now I don't know how it is in America, for example, but here in Germany most drills have a standardized collar behind the chuck that most of the time has the same diameter, and it can be used to fasten another handle, for example, or improvise a drill press if you have one of these drill stands. An exception are older Metabo drills, for example, where the collar has a different diameter, if I remember correctly. This drill stand doesn't really need to be repaired though, it's just very rusty. After cleaning it and putting it back together though, we can take a look at the rather beautiful mechanism. For a drill stand, it's rather sophisticated. The height of the drill can be adjusted, and it even has a depth gauge so you can read off how deep you are drilling into a workpiece. In case you're wondering what I'm doing with all these tools, by the way, I mean, does he really need another drill press? Well, in fact, you would be surprised how many tools I actually need, but the ones I don't need I will either give to friends or I will put them in storage, and maybe one day I will have the chance to actually open a store for used equipment. Actually, it's been a long-term dream of mine. Well, and when that day comes, I need some stock in order to be able to sell something, now won't I? But will that happen next year or in 10 years? Will it happen in Germany or maybe in another country? I simply can't say. Frankly, next to all the practical work that I'm doing here, there's little time to realize long-term dreams and plans. I guess what I'm saying is that I will need a team of people to help me with that. And I probably will have to do some community work here online to find those people, but I will talk a little more about that in a future video. As you can see, in the meantime I have already done some work on that coffee grinder. It's a Italian made, of course, and I think the biggest problem is that it has never been cleaned. But once I was able to get the actual grinder apart, I was able to clean everything. The old capacitor only has about 9 microfarads left of the rated 12.5 and should be replaced, but I simply don't have a fitting replacement at hand right now. So let's do a test with the old capacitor then. Now, I know it's a little messy and I'm certainly no barista, but it looks like ground coffee to me. Looks a little grainy also, but I guess that's just a matter of adjusting the grinder correctly. The next repair is also going to be a rather quick one, since there simply wasn't that much wrong with it. This item is interesting though, because I did not find this on the scrap, but bought it as a broken unit on eBay. Someone must have pulled this apart at some point, maybe because of a broken power cord or a bad contact, and then simply gave up. I think I paid around 15 euros for it, and let's see then if that was money well spent. This angle grinder is a fine brand, 1800 watt angle grinder made around 1990. It has a proprietary fine quick lock mechanism that has the advantage that you don't need any tools to change a disc, but it will also prohibit you from using anything but a disc on this grinder. I sure wouldn't know how to install a wire wheel here, for example. Again, much of this job required removing 30 years of dirt. It gets interesting though when you look inside the gearbox, where you can see why Fine is regarded by many as the highest quality tool brand there is. Just look at the number of bearings here and the quality of the gears inside this box. I sure like my Bosch grinders that I use a lot, but this one is on another level of quality. The switch and filters were actually just fine though. Some screws were missing and I had to make new ones to put the enclosure back together. And I guess I was just lucky that day. Let us take a look then at this old grinder stand. Now, first of all, what would this even be good for? Maybe you remember back in episode number 15, I repaired a number of smaller Bosch angle grinders, and then I installed one of them in this stand that allows you to use the grinder like a type of cut-off saw. And while it is really a useful thing to have, the size of the stock you can cut with a small angle grinder in that way is rather limited. But if you would be able to do the same thing with a bigger, more powerful grinder, now that would be a valuable addition to any workshop. Problem is that while you can get a small stand of okay quality for around 25 euros, a quality support for a bigger grinder is really expensive. Mind you, this price does not include the grinder. And, well, a couple of weeks ago when I was out on the road looking for a lathe, I explored this old workshop that had been lying dormant for a number of years. And in one corner I found this old AEG brand grinder stand. AEG was a well-known German manufacturer of everything ranging from household appliances over electronic components to power tools. My drill press, for example, was made by AEG. Today, you can still find mostly electronics products labeled AEG, but that is simply because the rights to the brand name still exist, but the original company does not. And that's just another example for a German quality manufacturer by name only. There is nothing really wrong with this device, and I'm simply cleaning it a little bit here. This fine angle grinder, as great as it is, does unfortunately not fit inside. If there's one thing I don't like about Fine is that they simply do too much proprietary stuff, which sometimes leads to compatibility issues. But maybe you remember the big red Hilti grinder that I repaired in one of the earlier episodes. It fits in there just fine. These screws here can be used to align the grinder properly so that it will cut at the right angle. Now, this is a great quality stand and paired with an equally great quality grinder. But there is one obvious problem here. You have to reach around to turn the grinder on and off, which is really awkward and not exactly safe to operate. So the task here is to find a permanent spot for this in the workshop and make it possible to turn it on and off smoothly and safely, and preferably from the front. And well, since there is a primitive soft start function implemented into the grinder's original power switch inside the handle, and since we will not be able to use that anymore if we switch this externally, then this also means that we have to build a soft start circuit, which we're going to do in a few minutes. So how did I go about this? Remember the forge that I built with parts from a scrapyard some time ago? I use it now and then, but the rest of the year it just takes up a lot of space in the workshop while not being of much use. But since I put a lot of effort into building it very ruggedly, it could also act as a part-time support structure for the grinder stand. In order to fit the stand onto the forge, I'm first cutting some plywood panels with a circular saw and screw these wooden parts together. The wooden adapter, if you will, fits onto the forge and will act as a ground plate for the stand. and a new on-off switch and emergency stop will be installed here as well. But first I spray paint the wood, because otherwise it would be ruined in no time, and after that paint had some time to dry, the grinder stand is bolted in place, and so are the enclosures for the switches and the soft start circuit. I'm now temporarily connecting the grinder directly to the switches just to show you how this is supposed to work. So you can switch the grinder on and off with that big rotary switch that is actually made for 3-phase motors, and the emergency button is just a kill switch that you can use to turn the grinder off quickly if needed. So you see, this works without limiting the starting current of the motor, which is what I refer to by using the term soft start. So why even add this soft start function? Well, there are several reasons. Let me explain. You probably can't see it in the footage, but each time I turn on the grinder, the lights in my workshop go off for a split second, and every other time the circuit breakers will be tripped. This happens because big universal motors will draw an enormous amount of current in the moment when they are switched on. Even if your circuit breakers are slow and not super sensitive, this still means an additional strain on all mechanical contacts, like the power switch, motor brushes, etc., essentially shortening the life expectancy of these parts. I'm sure many of you have also experienced power strips no longer working. This often happens because the contacts are charred. This doesn't only happen with universal motors, but for example also with big switch mode power supplies and also with big transformers, like this isolation transformer. I built this unit a few years ago, and you can see that after I push the button, it takes a moment until the device will turn on completely. The reason for that is that I inserted a starting current limiting circuit on the primary side of this isolation transformer when I built it. Without this circuit, the breakers would trip almost every time I turned this device on. So that is why I built 2 circuit boards and tested them with this setup. This is the circuit that I ended up using, with a big power resistor in that black left-hand enclosure. The power resistor is connected in series with the motor for a short moment until the red indicator LED lights up, essentially taking off the edge of the starting process. If you want to know how the circuit works, well, I'll explain that in just a minute. For now, it's time to test the grinder stand. Okay, let me try to explain how the circuit works that I built for this project. Here are the insides of an old Bosch angle grinder. Inside the handle we find a power resistor and a special kind of switch. A label on the outside tells us in German to push the switch all the way through. The reason for that is that the switch module actually contains 2 switches. When you start to push it in, the motor and the power resistor, which is connected in series to the motor, will be connected to the mains. The motor starts spinning up, but with somewhat reduced starting current and speed. By pushing it all the way through, the second switch is then shorting out the resistor, effectively removing it from the circuit. The motor is now connected directly to the grid and the grinder can run on full power. If you keep the power switch in the on position indefinitely, like we would do here, the internal resistor is without function and can't limit the starting current. So that's why it would be nice to have a circuit that does that automatically. We start with our universal motor. The dotted line here is supposed to indicate that the field coil of the motor is integrated into this component. We then have an on-off switch, which in this case will switch both line and neutral. And then we have our emergency stop button that will interrupt one of the conductors when pushed. This simple diagram basically describes the situation before we build the soft start circuit. And since we have to fit the entire circuit into this depiction here, we will need some more space. A power resistor is now connected in series with the motor. I used the resistor we found in that old Bosch angle grinder. It has 5 ohms, and from its size it could be rated at around 100 watts, even though it can handle much more than that for a few seconds, that is. Now, in older circuits of this type, I would now have inserted a relay here to short the resistor after a short moment. But this time we'll do it with a triac. The type is rated at 25 amps and is a snubberless triac, which is supposed to mean that it doesn't require a snubber circuit. Via 2 small resistors, it is then connected to an MOC 3061 optotriac. The optotriac will allow us to basically control this heavy electric load with the same ease with which we can control an ordinary LED. And on its input side, that is basically what this optotriac represents. It also has the additional feature that it will only switch the power triac in the moment that zero crossing occurs. If you don't want that feature, use the MOC 3021 instead. These 2 pins on the package will not be connected to anything. That's why I labeled them NC, as in not connected. The anode of the internal infrared LED is connected to a 470 ohms resistor, and it will eventually be connected to a low voltage power supply. The cathode is then connected to a small bipolar transistor that will be used to switch the optotriac on and off. In parallel to the optotriac, we also connect an ordinary LED. The circuit would work without it, but this will be an optical indicator showing us when the triac is supposed to be conducting. In order to power the optotriac and also a possible delay circuit, we still need a power supply, and that is why a small print transformer, output voltage 9 volts AC, is connected to the mains directly behind the switches. With the help of a single standard type diode, we can charge this mid-sized electrolytic capacitor. This minimalistic power supply will power everything else. 350 microfarads is an unusual value, but I have a lot of them lying around. You can use 470 as well, for example. Now, in my older delay circuits, I always use the NE555 timer here, and I tried it in this new configuration as well. Pin 3 is the output pin, and it is connected to the NPN transistor's base. The NE555 timer's output stage could handle this load without the need for an external transistor, but from the beginning I designed the circuit so that the NE555 could be thrown out if I would decide for another delay circuit. Pin 1 is ground, pin 4 and 8 are connected to the supply voltage. While pin 7 stays vacant, an RC circuit is connected to pin 6. The values of the capacitor and the resistors determines the duration of the delay. In this case, it's somewhere around a second. It's what I used in the isolation transformer as well. The datasheet then recommends to add a capacitor to pin 5, and also pin 2 is connected to pin 6. This very minimalistic circuit should be all you need, and I've used this successfully for years. However, it turns out that there is a problem with it. So here is the circuit that I built based on the NE555 timer. There are a few minor changes here to the circuit diagram. There is no power resistor installed here at the moment, so it will be just the triac being on or off. No resistor in series with the load. And then the electrical load is not a motor apparently, but this light bulb here, and this is just for test purposes so that you can see if it's on or not. So what I'm going to do now is that I will plug in the plug, and what is supposed to happen is that after I've plugged this in, a time delay of about a second should pass before the light bulb is switched on. Okay, so there was the delay. Let's do this again. Works just fine. But did you see that? There was like a small, short burst of light coming from the lamp the moment and again. So what happens here, seemingly at random, is that when I plug the plug into the socket, for the first moment the output pin of the NE555 timer is pulled to high rather than low, which means that the transistor will be conductive, the optocoupler will be activated, and then like the triac will also be conductive. So what happens is I plug this in, and there's a short moment where it actually conducts when it's not supposed to, you know, before the delay is actually starting. So this might have happened all the time, like in all the years that I've been using this circuit with relays, but the thing is that electromechanical relays are just much slower than triacs, and this short little burst would have been too short in order to activate the relay, and I just didn't notice it. So thing is, with this circuit, I've tried to get rid of this glitch. You know, people online said, yeah, maybe you should add like an RC circuit to the reset pin or change the capacitance of the, I think, on pin 5. So I've been poking around, I've tried to change all kinds of things about this layout, but then I decided, what the heck, man, I don't really even care about the NE555 timer that much, so let's just build a circuit from scratch where I know how it works and that will just do what I want it to do. Well, in case, of course, you know what the problem with the circuit is, let me know, but it's not like this is the only possible solution. Okay, so let's remove the NE555 from the circuit and follow another strategy. I connect another diode to the transformer's secondary. It will act as another half-wave rectifier, charging this RC circuit. That will provide us with a fixed time constant determined by the capacitor's and resistor's value. And now I'm connecting the capacitor to the non-inverting input of a comparator. The comparator's output is in turn connected to the transistor's base. The comparator also needs a resistor leading to the supply voltage, since it has an open collector output stage. And then a trim pot is connected to the inverting input of the comparator. So what the comparator is going to do is to compare. It will compare the fixed voltage at the inverting input, you know, the one labeled minus, to the rising voltage across the capacitor. And once the voltage across the capacitor is higher than the voltage at the tap of the trimmer potentiometer, the comparator will pull its output from low to high, essentially activating the triac. And I have built the second circuit up to this point. I put the power stage and the delay circuit on two different pieces of board here, just in case I have to redesign the delay stage several times. In this test you can basically ignore the light bulb, since the brightness difference caused by the series resistor is not visible here. Just focus on the red indicator LED that I have this time already soldered to the board. I plug the circuit in and the delay time passes and the LED lights up. Only problem is this works only one time, because now that the capacitor is charged and without any significant load on that capacitor, it will take way too long until it is discharged again. So next time you would turn your machine on, the soft start would not work. In other words, we have to add something that will discharge the capacitor automatically once it is shut off. And we can do that with the second comparator that is housed inside that little package anyway. They usually come as dual comparators in one package. Via another diode and a resistor that will limit the current through the output stage, the second comparator will discharge this capacitor. But how will it know when to do that? Well, I'm adding yet another diode to the transformer secondary. This time it will charge a smaller electrolytic capacitor with only 10 microfarads. And in addition, I'm putting a sort of bleeder resistor in parallel that will drain that capacitor once the transformer is switched off via the on-off switch. And on the inverting input, we will then again have another trim pot where you can set another fixed voltage. Well, at least this voltage coming from the much bigger 350 microfarads capacitor will be more or less fixed for much longer than the voltage at the much smaller 10 microfarad cap with the bleeder resistor. So in other words, when the circuit is turned on, there is a delay until the capacitor reaches a voltage threshold defined by the setting of the first trim pot. And as you pull the plug, the second comparator switches to low and drains the capacitor. When you plug the circuit back in, the process begins anew. In a final step, the two boards were then merged together, and the power resistors I had first used were replaced by the bulkier external power resistor. So maybe that might seem like a lot of effort to solve such a simple problem. And there are tons of other ways you could do this. But no matter if your solution is a little unusual, it feels really good if you're able to build something that works the way you only thought it would in your head not too long before. So as always, I hope that you appreciate what I had to show you here this time. And if that is the case, then please give this video a like to let me know that you want to see more of these Scrapyard videos in the future. And in case you want to support this channel more actively, you can make a donation via PayPal. An email address for that is in the video description. Or become a supporter on patreon.com/tpai. See you soon.